professor at USC. One of my favorite researchers, spans both applied and theoretical machine learning, and I think this talk may do a little bit of both. So thanks for being here.
Thanks a lot for that introduction, and great to be here. So thanks for inviting me. So I'll mostly talk about prompt tuning. Misha unfortunately has heard this multiple times, but I think the rest of you haven't. I'll kind of do, if there's time, I'll briefly mention how we're using these kind of prompt tuning techniques in more scientific domains more recently. That is maybe the new part. I was originally going to talk about something else, but as always, my proofs are running behind. But luckily, most of you have not heard this, so it's okay. So this is joint work with Sam at OIMAC, who's now at Michigan, Christos at UBC, and Ankit, who is at Google. So let me actually kind of motivate prompt tuning a little bit. So we all know about fine tuning, right? Like we've heard about it multiple times, right? It's this idea that you take a foundation model that is generically trained on a lot of data. If you have like a downstream application, you kind of try to fine tune it, right? So if you have like table to text, you fine tune it. If you have summarization, you fine tune it, and so on. And of course, this is a very costly endeavor because you kind of need to store and train a full model for each task, right? So both compute and storage is heavy, so that is the key issue. So like the last few years, we've kind of witnessed methods to combat this, right? So one thing that is very popular was popularized by Percy Leon's group is like this idea of prefix tuning, which is like you add some extra training parameters toward the input of your network, right? And you kind of like train those, right? So now for each downstream task, you kind of train only a few parameters toward the input of your network. And so you can imagine this is much lighter weight. Storage-wise, it's much less expensive because you're only training very few parameters. Compute-wise, it's also less expensive, but not as clear because you still backprop through the entire network. So there is savings, but still maybe not as significant, but still quite a bit of saving both on compute and storage. But one of the surprises here is that it actually also works better. So it actually improves the BLEU scores, right? And so this is one way you can kind of start seeing that a surprising phenomenon appear. And then basically this is the basis of my talk is this prompt tuning paper in 2021, where now instead of adding extra parameters at the beginning of your network, what you actually do is you add extra trainable parameters to the input of your network, which you can also view it as like actually running gradient descent on the prompt, if you will, right? So you add extra parameters to the input of your network. I'll go over the exact pipeline later, but the surprise in this paper is that especially as the model size grows, as the foundation base model parameters grow, at some point, this idea of prompt tuning actually is going to beat actual fine tuning, which is really surprising. So you have fewer parameters. It's computationally and storage-wise more efficient, but it also gives you better accuracy. Yeah. So fine tuning is you fine tune all of the parameters. Prompt tuning, you add extra inputs to your network, which you train over. And I'll go over the exact pipeline in detail in a specific network, so it becomes more clear. Go ahead.
When you add the extra soft tokens that you optimize, do you also optimize the weights of the network?
No, just the token. I mean, presumably you could mix and match. You could fine tune a little bit. We haven't done that. Yeah.
So no weight updates.
No weight updates at all. It's just the extra parameters. This is why it's surprising, right? So we want to kind of demystify this. I'll go over all the details now, because I don't know the background of everybody. We'll talk about what prompting is, what prompt tuning is in more detail, but that is like the high level premise. So what is prompting, right? So language prompting, at this point we're very familiar with it because we play around with GPT stuff, right? It's the idea of like we steer the behavioral language model to have desired outcomes, right? So they say that the actual task is translate from English to French, right? And then there are various ways of prompting it to do this. One way is through like giving it examples. You can think of this as the prompt, right? So you prompt a model to get the desired outcome, right? And this was, of course, popularized in the original GPT paper, right? One of the cool things that I think is maybe lesser known, that this also works pretty well in the visual domain. So you can also do this in the visual domain. Again, basically you add a visual prompt, like maybe a color palette or something, and then even though the base surface, this idea of prompting works very well, it improves the accuracy. And again, prompt tuning in this context is that, okay, so why don't I actually optimize over these extra inputs, right? So the base are frozen, but I'm actually optimizing over this extra inputs, right? So this is what we want to demystify. So we're only fine tuning these extra parameters. And so if we want to understand this theoretically, there's a couple of things that are interesting here. One is like from like an expressivity viewpoint, right? It's a legitimate question to ask. You're kind of updating this very few parameters. What is the expressive power of doing this, right? Is it cases where it actually does better, theoretically better than fine tuning? And then, given that go ahead, Misha. Sorry? So you run gradient descent. It's just you view it as parameters. So just the whole prompt. Yeah. The whole prompt you view it as extra input. Parameters that you run gradient descent on. You could also run what is known as hard prompts, which is you also want to make sure that the prompts make sense in language or vision. So there are ways to doing that, but in the simplest case, it could be complete gibberish, but it just helps. Yeah, that's the idea. And then, I'm always interested in actually understanding the dynamics. The other question is like, okay, maybe in principle you could achieve more, but if you were to actually run gradient descent, does it do well, right? And what does the dynamics look like? Does it generalize and so on? So these are challenges from a theoretical perspective. Go ahead.
When you tune the prompt, you tune the embedding, right? So it's not actual tokens anymore.
Well, no, you actually tokens. You could do it also in embedding space, I think, but we actually work with the tokens.
Yeah. Yes, so there's no updating the weights.
Yeah, nothing gets updated, right?
So you just run it over but tokens is embedded or just tokens?
Yeah, I'll show it. I mean, so in the simple model that I have, I don't have the discussion of tokens, but the embeddings. But you also, for us in the real experiments, you also freeze the embedding layers. So there's really just inputs. But yeah, of course, in a simple network, we don't have embeddings, right? So basically, but then we go over like what the simplified model is. So of course we have tokens, right? Just as a reminder, tokens in the context of language is like basically words, or in reality pieces of a word that you have some embedding of, right? And then in the context of vision, the tokens would actually be image patches, right? So out of this, you kind of create a data matrix where, on one side tokens, one side the dimension, right? In this pixel example, the rows would be like pixelated things of the patches, right? So that's kind of the input to your transformer. So we focus on a very simple model, which is a single head attention. Before I explain what prompt tuning is in this context, let's go over the architecture, right? So you have this input tokens in the form of this matrix. You pass it for a query, key, and value matrix, right? Via a self-attention mechanism, right? Like you have this product of the query, key values. You pass it through like attention, which here in this notation is row-wise, and then you combine these to get the output. So if you're doing classification, you would also typically scalarize, right, to get a either one hot encoded or a 1D output. If you're doing regression, so that is the model. So in this context, what does prompt tuning do? Prompt tuning, again, it's this idea, like you freeze the weights, you're adding extra parameters to the input. So these are here. So it's actually literally extra tokens at the input, right? And then, typically also you mask the prompt from some of these matrices. So you don't actually hit it with all of these matrices. Actually, typically you do this for the query matrix. So you keep it in a query matrix, so you don't see the effect of these in other parts. And so then if you again write down the self-attention model, it looks something like this. If you kind of expand the terms, the details are not super important. there's actually going to be two terms. One term that is frozen because of self-attention. This is the part that you're not fine-tuning, you're not touching the base or fixed. There's a novel term where these extra prompt parameter shows up, and that's what we're going to focus on. We will call it prompt attention. So to simplify the model a little bit further, I want to mention that even though we are coming at this formulation from a self-attention kind of mechanism, this is also how the original attention mechanism, right, before transformers is based on this phenomena. And I'll explain why that is. So, but the original attention papers were not self-attention. They were actually of this kind. So even from that standpoint, it's an interesting object to study. And let me explain the logic behind that. So here, again, the idea, remember, the inputs are tokens, right? The rows are tokens, d-dimensional tokens. You have capital T of them. So what is this doing? This is kind of like assigning relevance scores based on like the query. Here for us is a prompt, but based on the query, you kind of assign relevance scores to different tokens. Then this X transpose SXQ is kind of blending, right, the tokens according to these relevances. And then you have a trainable head. So you can see even in a natural setting, this makes a lot of sense. So both W and Q, right? So but in our case, like Q really originates from prompt. Usually it might originate from query in the original attention models, right? And this is why we call it prompt attention. It's a made-up name, but it works. So if we are going to present some analysis, unfortunately, I have to give you a data model. So this is going to be a little bit painful. So let me just set it up by saying that you can think of this as some sort of equivalence of Gaussian mixture models for this kind of setting. So I'll go over this slide first. It's not here, it might look a little bit ugly, but I'll kind of explain it for visualization in the next slide. So bear with me in this slide. If things don't make sense, don't worry too much. So we're going to assume the data is IID. In learning theory, that's what we do. So we're going to assume the labels are plus minus 1, IID with probability 1/2, right? So conditional on these labels, we're going to assume the tokens come from a certain distribution. So we're going to have tokens that are relevant to what you're trying to do. So these are context relevant tokens. You're going to have irrelevant tokens. The irrelevant tokens be essentially model at noise. I'll kind of tell you more about that. And the ratio of relevant to irrelevant, you can kind of think about it as some sort of sparsity. I have to fit that in somehow in every talk, right? So because of my background. But the relevant tokens, we're going to assume they consist of two things. They're context relevant, right? And there are things that relate to making the decision for the classifier. Again, these becomes more clear in the slide because I'll give you a more intuitive interpretation. And as I said, the non-relevant tokens, you can view them as Gaussian noise essentially, but there's some leakage potentially from the context stuff. Okay, this may seem like a weird model, so let me kind of try to intuitively try to justify why this kind of makes sense. So going back to like the the image case, right? So remember, our tokens are patches, right? So what does context relevant tokens mean here is like things that tell you that this is a bird, right? So you have patches that like the beak, the feather, tell you, oh, this is kind of like a bird, right? And then you have context irrelevant stuff like the sky, the water, right? These are irrelevant patches, right? So now among the relevant ones, right, there are patches that kind of guide you toward making the classification decision, but the ones that are, though it helps you tell you the bird, it doesn't in this case tell you what kind of a bird, right? Like in this case, we're trying to, let's say, classify breeding versus non-breeding kind. So the beak part will tell you it's a bird, but it's not so relevant for our classification task. So here what happens is the breeding kind have like a more orange feathers and blacker bellies, right? And so you can see those are those. So you can view this as kind of like the context. This is kind of what helps you make the classification decision, right? And so this is exactly kind of our model. Of course, in a realistic setup, maybe this happens as after a deep embedding of some sort, right? But yeah, so there's some justification that this model makes sense. Again, you can kind of view it as a measure of a Gaussian model for this kind of setting. of course, this is more tailored toward images, right? Like if you want to do language, probably we need a better model. We're actually thinking about that with some people here. So okay, so back to the theoretical challenges that we started with, right? Like the expressivity one, right? Can this kind of simplified model be expressive, right? So in order to do this, we're going to compare this with some baseline models. So this is the prompt attention model. Notice that we have 2D trainable parameters because of the way we set it up. You can imagine a very simplified model where you just mix all of the tokens equally and just, to do a linear model. So this has D parameters. You can have a full-on self-attention model. This is like would correspond to fine-tuning over everything. This would have D square parameters, right? Even a little bit more, right? But already here you have D square. And then finally, you could say, okay, what if I just get rid of the nonlinearity? This is a bilinear model, right? So this would also have 2D parameters. So for training, of course, we use empirical risk minimization with least squares loss for technical reasons, and we care about classification error, right? So here is like the kind of like the first theoretical result here, which is more to the expressivity question. For simplicity, I'm going to even assume the noise, if the context irrelevant stuff, the noise is 0. But this theorem basically tells you that there is a distribution over these leakage parameters such that if I were actually to find the global optimum, let's forget about the dynamics for a second. If I were to find the global optimum of the empirical loss, self-attention can at most achieve 50% accuracy. So actually self-attention, even though it has these square parameters, it would actually fail in the simple model. Bilinear does even worse, can at most achieve 25% accuracy. Whereas the global optimum of the model that we're studying, right, like this prompt attention model, for any distribution of these leakage parameters would actually achieve 100% accuracy. So it at least tells you that in some settings, actually this kind of prompting model and this kind of prompt tuning idea can in fact be much more expressive, right? And can do a much better job even compared to full on self-attention. So like prompt tuning can be superior to fine tuning in some sense. So here is some kind of high level intuition on how you would construct these counterexamples. Like if you view these things in a relevance, context relevance, label relevance kind of domain, this is where the good stuff is. These are places where all the different models actually fail. So very high level, this is how we kind of construct these counterexamples. Yeah.
Q star and just different parameters.
Yeah, the Q star and W star are the ground context and stuff. And then, we have these leakage. Here, what I'm demonstrating is, where can you place the leakage to make self-attention fail? Where can you place the leakage distribution for like the bilinear model to fail and so on? Yeah. Go ahead.
Is this what was the task?
So this is classification, right? It's a binary classification. So yeah.
So then even random labels would get 50% accuracy. So
Yeah. So, but this is what we're saying, right? Like if you actually were to find a global optimum, it does worse. So it is what it is, right? Yeah, it's sad. So it's actually doing worse than random guessing. Yes. Go ahead.
Sorry if this is a silly question. Is the context relevance dependent on the prompt or is it conditioned on like the label?
These are fixed vectors, right? Like the Q star and W star are fixed vectors. So it doesn't depend on anything.
Okay.
Prompt is something you train over here, remember? So yeah.
So like when you say like context relevance, like what exactly?
So it's like these vectors. Sorry, maybe it's not clear. Well, maybe here, like the relevant tokens, right, has a context vector plus -1 a regressor vector, right? So again, the idea is there that this regressor vector is what allows you to do the binary classification. This is the context. Like this tells you that it's a bird. This is kind of telling you whether it's a breeding kind or a non-breeding kind, right?
Okay, thank you.
So they're fixed vectors. We don't, but probably you can construct it, right? Yeah. So it's not going to be in this model because for this model, you always get 100% accuracy, right? Yeah. Yeah, we're not trying to say like this is always better, right? There are some cases where it's better. And then, of course, then there's a question of like, what happens if I actually run gradient descent, right? Can I also recover this stuff, not just for the global optimum, right? But as I'm running gradient descent, can I get similar results? And there, we actually didn't analyze the full trajectory of gradient descent. We essentially have analyzed like just doing 3 steps, right? I'll kind of like maybe come back to the idea of this proof. But the idea is that the first step kind of estimates W star. The second step with a larger learning rate estimates kind of Q star. And then the last iteration on W refines your initial estimate of W. This is actually necessary for things to work. So if you do this 3-step gradient descent kind of approach, basically if you have number of samples that are linear in dimension, then something really interesting happens, which is like you can pick the step size so that for any epsilon, right? So epsilon, you can think of it as a small number. The attention waves perfectly pick the relevant tokens. What do I mean by that? This means that on the relevant tokens, you essentially pay uniform weights, like 1/t, because think of epsilon as going to 0. On the irrelevant ones, you pay no attention to them, right? It's epsilon, think again, going to 0, and you can make epsilon arbitrarily small here, right? So that is the idea. So this is really, I think, the most insightful part of our result, that the attention does what it's supposed to. It picks the relevant tokens when you run gradient descent. But in terms of the actual final error, you could also calculate that. This is an upper bound. You can see this is far superior to any of the other models that we studied. In particular, if you do compared to a linear one, if the context is sufficiently large, like this normal disk Q star is sufficiently large, this is much better, for example, than a linear model. So that is the idea. But again, I think the most interesting part is the part that says that attention is actually doing what it's supposed to do, is picking relevant out of all of these tokens. It actually is picking the relevant ones. And so that is really the key idea of when Q star is sufficiently large, you pick the relevant tokens, you ignore the irrelevant ones. And this is what in the literature is known as this idea of hardening of softmax, right? And this is why you kind of see sparsity of the attention maps. And this actually really does work in kind of practice. So this is a toy example. I'll kind of show from other papers more realistic examples. But here we're taking CFAR images. We're randomly embedding it in just pure noise, right? ImageNet noise. So this is fine-tuning baseline. This is if you do various kinds of prompt tuning, like this is kind of our version. The blue one is the version from the prompt tuning paper. This is really prefix tuning, the first one. But basically, you can see that various forms of prompt tuning actually do better. At least these new 2 versions do better than just fine tuning in this very simple example. But maybe that part has been already demonstrated quite well. But the more interesting part is that if you look at the attention base, they actually do pick the relevant information, right? So in this case, you have these images embedded in random noise. If you look at the attention base of the last layers, they actually pick the relevant things. And so this is really the main insight, is that by updating the prompt, what you're really doing, you're steering the attention mechanism to pick the relevant contextual information. And once you kind of pick the relevant tokens, then classification becomes easy, right? So that is the idea. And you can see this actually bears out in practice as well. So, and, like since, did this over the past year, there's actually more and more evidence that this is happening, right? So this is a really interesting paper. This is last year. Basically, that shows that prompt tuning leads to actually more robust features, right? So if you do prompt tuning versus not doing prompt tuning, the attention maps look more reasonable, more interpretable, and you do learn better features. So this is kind of an extra motivation that this whole strategy is reasonable. So Like very briefly, I just want to mention, I'm not a vision or an NLP person, but I do like application sciences a lot. What we're doing now is actually using some of these prompting ideas in Cryo-ET. So this is actually very recent work, joint work with Simon and Reinhardt from TUM and Zalon, who's at USC. He's, by the way, going to be on the faculty job market, and he's incredible. So I don't want to get too much into the details of what Cryo-ET is, but essentially it's a technology that allows you to image protein structures at live as they're interacting, right? So that is the special part. Even compared to Cryo-EM, you can capture the interaction, but it comes with, it in particular, most famously, it was also critical in the design of the COVID, vaccines. One reason they could do it is because you could do these images very finely. It's a very complicated pipeline. There's a lot to do for machine learning here. You have to prepare the sample, you have to do imaging, kind of like a tomography kind of setup. It's also very challenging from an imaging standpoint because they're missing wedges. But at the end, even if you do images, you have to kind of pick some particles and then denoise them, right? So we're actually working kind of on the entire pipeline. But maybe today I'll briefly tell you how prompting is helpful in this case, right? Like this in the particle picking portion. So we're focusing on a very small part of this huge pipeline that we're working on. But even this small part is quite tricky because, again, the images are extremely noisy. Like you're supposed to pick the particles, right? So that is the idea. So it's kind of a 3D object detection problem, but it has very low SNR, and there's a lot of proteins in a single image, right? So like 20K sometimes, right? So it's a very complex task. And so high level, what we're actually doing, we're kind of training a foundation model, like something like SAM, if you will, and then using prompting to kind of fine tune a prompt encoder. And that is kind of the basic idea. So this is, I believe, the first time like a foundation model approach has been applied to this particle picking problem. And, so this actually ends up working well. I don't want to bore you with the details, but it turns out compared to the state of the art, you achieve on par accuracy, but you can do it much more quickly. It's really important in this application. And you can do it with much less fine-tuning data. So, but yeah, this was kind of a tangent. I'm practically out of time, right? Or okay, perfect. So I'll kind of tell you a little bit about how these proofs work, because there's actually an interesting connection to Simon's Institute and Adam. Originally. The basic idea, and this is why we look at the initial trajectory of gradient descent, right, is that, and this is something that I did not appreciate, even though I worked on this like 7 years ago, that for analyzing a lot of non-convex problems, the first few iterations of gradient descent actually have quite a bit of signal. So there is kind of a spectral bias, right, which you can utilize to analyze these algorithms. And let me demonstrate it in a very simple example. This is actually the example that I worked on when I was a fellow 7 years ago at Simon's Institute, which is like a simple single index model. They're very in vogue right now, but funnily enough, I started working on this because Adam gave a talk on learning reuse using kernel methods. I was already working on learning one hidden layer neural networks, but I didn't realize even the simpler case was, there was a lot of interesting things to do. So it's about learning single index models. So why is it that the first few iterations is very effective here? Even though I will tell you, like in this case, this proof strategy, again, fast forward like 7 years, more recently we figured out, okay, it's actually very good for other problems like low rank recovery, one hidden layers. This is the paper that most people know about with Jason and Alex. And again, same strategy here for prompt tuning. So why is this helpful? Because imagine you're doing a nonlinear least squares, you're just running gradient descent, right? So in the single index model, even if you take one iteration, that's already very valuable, starting from 0. So if you use small random initialization, this part goes away. So you just have weighted some of your gradients at 0. So in the single index model, this takes a particularly simple form. So it's kind of an empirical average like this. If you replace this with a population average, you basically get the output of the planted model times X. But assuming Gaussian data, you have Stein's lemma, right? So Stein's lemma says that this kind of expectation you can replace with the gradient over X. So the gradient over X is actually very simple. Of this link function is just theta star, right? So already the first iteration actually gives you the answer, right? At least if you had infinitely many samples. It's not perfect, so empirically it will give it, right? But that was kind of the basic idea in the, that simple paper that I literally wrote over a weekend 7 years ago. Yeah, that's the idea. Of course, yeah, exactly. Because I was working on phase retrieval, and then I heard that talk. It's like, okay, the ReLU should be easier because you don't lose any information, right? Because the monotonic activation, phase retrieval is symmetric. Yeah, exactly. But for other models, it's much more complicated because for example, for like something like actually phase retrieval or a low rank recovery, what happens is that the gradient also vanishes. So then you have to do more work. You cannot just analyze one iteration. You have to actually analyze a few iterations, right? But still, that's the basic idea. I think I managed to kind of convince some of the more recent fellows to get interested in this. So maybe there will be more outcomes from the Steinmetz Institute on this sort of problem. So in prompt attention, it's kind of a similar idea, but you do need the free steps because of all the refinements that is needed. So again, you estimate W star, you estimate Q star, then you refine. But the reason is here is a little bit complicated. The first step is not complicated. It's actually, I won't go over the details, but it's kind of a simple concentration because a lot of things are zero. It's actually not bad. It's just like linear in the Gaussian noise. So the first step is actually fairly easy to do, and concentrate. The tricky parts becomes like the second and first step. I will not go over it, but you can imagine there are 4 X's here, right? So concentration or calculating the population is non-trivial, right? So X, remember, depends on Gaussian noise. So this is a very non-trivial calculation. Even concentration is very tricky. Notice that we got linear sample complexity, right? So you do actually have to use quite a bit of fancy concentration arguments here, but I will not bore you with those details. So let me actually wrap up. So what I talked about is kind of initiated a theoretical investigation of these original attention models and prompt tuning. You can think of this as a simple non-linear kind of bilinear model. So the messages were that attentions enable selection of relevant tokens. And in some cases, we also showed that it's provably superior. We also had some dynamical results. There's a lot of interesting questions to ask, right? Like you can ask multiple head, all sorts of ways to extend this model. And I think even in this basic model, there's a lot of interesting things to ask about. You could potentially use this as a basis of understanding self-attention more clearly and so on. Okay, with that, let me end it here.
Time for, we do have time for one question while I'll say, yes, that's it. Yeah.
Thank you so much for your awesome talk. Would you expect significantly, I know the theory might not be as straightforward, would you expect significantly different results using electron entropy loss?
Well, yeah, here would be logistic loss. We have not looked at it. I think you just need a little bit different assumptions, margin assumptions, and so on. We have not looked at it. I think the theory is going to be helpful, but you still need to do more. Yeah.
Thank you for your prompt attention.
Yeah.
Okay, thanks again.